Hello, my name is Ori Peled. I'd like first of all to thank the committee for considering our work for the Jack Wolf Student Paper Award. This work was done alongside Oron Sabag and Professor Chaim Perlmutter, my supervisor. I'd like to talk today about the feedback capacity and coding scheme for the 0K RLL input constrained binary erasure channel. Our system model is displayed in the following figure. We see a binary erasure channel with a noiseless feedback link from the channel output back to the encoder, meaning that at time I, the encoder has access to all previous channel outputs. The channel itself is a binary erasure channel with an erasure probability denoted epsilon. The input sequences to the channel are constrained in the following way. The sequences can contain at most k consecutive zeros. That is, of course, the 0k RLL constraint. As far as motivation, information theory has two prevailing approaches for dealing with transmission of information over noisy channels. The first approach, which I would like to call the statistical approach, has us studying the channel and particularly its statistical properties and modeling it usually as a memoryless channel and then trying to calculate its capacity. The second approach, I'd like to call the constraint approach, is where we study the channel and notice that if we manage to avoid certain input patterns in the input to the channel, then it in fact becomes a noise-free channel. In our research, we wanted to combine these two approaches by having a simple binary erasure channel as a model for a noisy channel and using an RLL constraint for the input to the channel. The DK RLL constraints are very common in many recording standards, such as magnetic and optic standards. Even the modern QR codes contain elements of the DK RLL constraints. The non-feedback capacity for our system model is as of yet unknown. Several works have been made to provide various bounds on the non-feedback capacity, but the capacity itself is still unknown. Of course, the feedback capacity is an upper bound for the non-feedback capacity, and that's one of the reasons that we chose to study the case with feedback. So the goal for today is to discuss the capacity and coding scheme for the 0K RLL problem with feedback. So without further ado, this is our main result. The feedback capacity of the 0K RLL input constrained binary erasure channel is given by the maximization over this function. In this function, h2 of a variable is simply the binary entropy function. Epsilon is the same parameter of channel erasure, where epsilon bar is simply our notation for 1 minus epsilon. Notice that the function itself seems to be a function of k variables, denoted delta 0 through delta k minus 1, but the maximization is done only over a single parameter, delta k minus 1. That is because the rest of the deltas can be calculated recursively once we have maximized over delta k minus 1. In future slides, instead of again writing in this entire big expression for the capacity, I would simply address this function as r epsilon of delta k minus 1. Let's consider a few graphs of the capacity as a function of epsilon for several values of k. First of all, the black solid line is the unconstrained capacity, which is of course 1 minus epsilon for the binary erasure channel. The blue dashed line is the capacity we get for k equals 1. The capacity expression itself is on the bottom left corner. The red dotted line is the capacity for the case of k equals 2, and the purple line is the capacity for k equals 3. As is evident in this figure, as k increases, the capacity becomes closer to that of the unconstrained channel. That is to be expected, since as k increases, the constraint itself becomes more and more lenient and closer to the unconstrained case. Thus, this behavior is to be expected. I'd like to start discussing the coding scheme. It is inspired by the concept of posterior matching introduced by Shayevitz and Feder in 2011, and is constructed mainly of two ingredients. I would like to explain the first ingredient using a simple example of a binary erasure channel with no input constraint at all in the presence of noiseless feedback. So, first of all, we take all 2 to the NR possible messages and map them uniformly to message points inside the unit interval. Second step is to introduce the labeling, which is simply a function that assigns the label 0 to part of the unit interval and the label 1 to the rest of the unit interval. The input to the channel at time t is a function of the actual message we want to transmit and of the labeling we employ L. So let's say we want to transmit the black dot out of the entire message points. Since it lies within the subinterval denoted with 0 by the labeling, then the first channel input would be x of 1 equals to 0. In the case of the binary erasure channel, in the presence of feedback, we know that the repetition code is a capacity achieving coding scheme. So if the first output symbol is an erasure, we simply repeat the same transmission again. So again, x of 2 will be equal to 0. An important property of the binary erasure channel is that if the output symbol is not an erasure, then the output symbol is equal to the input symbol. We can exploit this property by saying that if the output symbol is not an erasure, then the decoder can eliminate from the set of possible messages all messages that were labeled with the opposite symbol. So in this example, the output symbol was a 0, so the encoder and decoder can eliminate from the set of possible messages all messages that were labeled with 1. Then both encoder and decoder take the set of remaining possible messages, stretch them again across the unit interval in a uniform fashion, and continue with the transmission process. The process shall terminate when the size of the set of possible messages is equal to 1, in which case the decoder simply declares the only remaining message to be the correct one. Notice that in the above example, we have transmitted 3 zeros in a row. So if I were to impose a 0-2 RLL constraint on the input to the channel, then this coding scheme would surely violate the constraint, since we transmitted 3 zeros in a row. This tells us that once we impose input constraints on the system, then we can no longer use a simple repetition code as in the simple case that we saw here. We must move to what we call adaptive labeling, where the labeling at time time t plus 1 is a function of the labeling at time t and the channel output at time t. Please notice that these two items of information are available at all times to the encoder and to the decoder. Thus, both parties can agree upon the employed labeling throughout the transmission process. The second ingredient of the coding scheme is a state machine that governs the way that the labelings progress throughout the transmission process. So in this graph, the edges correspond to channel outputs, and the nodes correspond to labelings. As we can see, we have k plus 1 labelings called L0 through Lk. Each one of these labelings, Li, has a parameter associated with it we call delta I, which simply determines the partition between the part labeled 0 and the part labeled 1. The exception to this rule is the labeling denoted L tilde of 0. It uses the parameter delta 0 to determine where to put the 1 and the 0, but it does so in an opposite way of all the previous labelings. Namely, the part that is labeled with 0 starts at 1 minus delta 0 and culminates in the end of the unit interval. We arrived at this particular state machine for our coding scheme first by running a few numerical dynamic programming simulations for a few small k's, And then from those simulations we were able to deduce the general principle that the coding scheme follows and generalize it to the coding scheme you see before you for any natural K. So one interesting thing to notice about the about the coding scheme is the only way to arrive at labeling LK is if K consecutive channel outputs were zeros. So this tells us that in order not to violate the constraint, labeling LK must denote the entire unit interval with the label 1 so as not to transmit another 0. Another interesting property is that whenever a channel output is a 1, the system turns back to labeling L0. Let's show with a few examples how this coding scheme operates. Let's say we started labeling L0 and we want to transmit the black dot. We will of course transmit x1 equals 0. If the channel output is not an erasure, then as the graph dictates, we move to channeling L1, and since now the black dot lies to the right of the parameter delta 1, we shall transmit x time 2 equals 1. Another example of an erase symbol. Let's start again at the beginning in L0, and we want to transmit the black dot, and the first channel output is an erasure. We now transition to labeling L tilde of 0, and the same black dotted message is now lie within the subinterval denoted 1. So the next channel input x of time 2 will be equal to 1. If that symbol arrives without an erasure at the output, then we transition back to labeling L0, and since the black dotted message now lies to the right of the parameter delta 0, we will transmit x3 equals 1 and continue the transmission process. It is clear that not every choice of parameters would yield a coding scheme that complies with a 0k input constraint. However, it can be shown that if we chose delta I to be at most 1/2 for all I, then the constraint is satisfied. An interesting observation to note is that for the optimal k-tuple, denoted here delta 0 star through delta k minus 1 star, we have that the sequence of deltas are not increasing with the index. That result is reasonable, since recall that the parameter delta I is simply the probability of transmitting x equals 0 while employing labeling Li. So as we progress in the indexes, the system as a whole comes closer and closer to the point where it is constrained. If the system reaches the constraint, then it is penalized by having to use a transmission to avoid violating the constraint, while benefiting not at all from this transmission. That is why, as the system approaches the constraint, it is reasonable to expect that we would like to have a smaller and smaller probability of transmitting a 0. The rate of the scheme is of course defined by the expected number of information bits per number of channel uses, and using arguments from stationary probability of Markov chains, we can prove that the rate achieved by this scheme is a lower bound for the feedback capacity. That the feedback capacity is lower bounded by the same function that we earlier denoted with R epsilon delta k minus 1, and of course is also bounded from below by the maximization of the same function. Let's now start talking about the method of proving the upper bound. In order to do so, I would like to introduce the non-causal setting of our problem. So let's say that one of your 3 wishes is to know in advance whether or not an erasure is about to occur in the upcoming transmission. So the genie decides to grant you this wish, and now the encoder has non-causal knowledge about whether or not the upcoming transmission is about to be erased or not, which is governed by the random variable theta. Clearly, the feedback capacity, the non-causal capacity is not inferior to the feedback capacity. When we try to provide an upper bound for the non-causal capacity, it is sufficient to consider only codes where if theta I equals an erasure, then the encoder transmit xi equals 1. That's a reasonable assumption or a reasonable choice because the 0k RLL constraint does not impose any restrictions upon the number of ones we are allowed to transmit to the channel. Using, again, arguments from stationary of Markov chains and this time also method of types, we can show that the maximum of the function previously denoted R epsilon delta k minus 1 provide an upper bound for the non-causal capacity. This method gave us the bonus result that as far as the 0k RLL constrained binary erasure channel, we have that the feedback capacity is in fact equal to the non-causal capacity. A natural question arises, is this always the case? Meaning that is the feedback capacity always equal to the non-causal capacity for every input constraint? So the simple answer for this question is no, and I would like to demonstrate it by showing the same problem setting, but with a slightly different input constraint, the to infinity RLL constraint, where every one transmitted must be followed by 2 zeros. The non-causal capacity for this setting is given by this expression, while the feedback capacity is given by this expression. A graph of these two expressions is a function of epsilon. Shows us that the non-causal capacity for this input constraint is strictly larger than the feedback capacity. So this example shows us that we can not always hope to find a tight upper bound for the feedback capacity simply by considering the non-causal capacity. So we must have a different approach for these types of constraints. A second method for providing an upper bound is what we call the utilization of a Q-graph. First of all, let me please define an S-graph simply as a representation of a constraint. So, for example, if we use the 0-2 RLL constraint, then this graph is a representation of the 0-2 RLL constraint, meaning that every binary sequence that satisfies the 0-2 RLL constraint can be constructed by some walk over the labeled edges of this graph. A Q-graph is an irreducible directed graph where each node has a size of alphabet y outgoing labeled edges. In our case, of course, the alphabet of y is 0, 1, and question mark. And an example for a Q-graph can be this Q-graph. It is an irreducible graph, and each edge has 3 outgoing labeled edges. Each node has 3 outgoing labeled edges. This method of proving an upper bound consists of an algorithm that takes an S-graph representing the constraint and a proposed Q-graph and turns it into a coupled SQ graph. The upper bound, introduced by Sabat, Perlmutter, and Feistel this year, tells us that the feedback capacity is upper bounded by the supremum of this conditional mutual information. The joined distribution is written below, where pi SQ is simply the stationary distribution of the above-mentioned SQ graph. So any Q-graph leads to an upper bound. A smart choice of a Q-graph will lead to a tight upper bound. The example we have shown in the previous slide of this Q-graph actually leads to a tight upper bound specifically for the 0-2 RLL case. So in this method, we were able to compute an upper bound for the feedback capacity without reverting to the non-feedback capacity at all. To sum up, we have seen posterior matching inspired coding scheme for the 0k RLL binary erasure channel. We have talked about 2 methods of proof for an upper bound. One of these methods provided us with the insight that for the 0k input constraint, the feedback capacity is equal to the non-causal capacity, while we have seen an example where this is not the case for a different input constraint. We have worked out the capacity encoding scheme for the 1-2 RLL binary erasure channel. That constraint is simply says that everyone must be followed by a 0, but no more than 2 consecutive zeros are allowed. We have not presented this result in this presentation today. As far as future research is considered, we would like to find the feedback capacity for the general case of any parameters d and k, and perhaps tackle the non-feedback capacity. Thank you very much.